Have you ever wondered what the coldest place on Earth is? Well, I can guarantee it's not where you think. It's not the South Pole, it's not the top of Everest, it's not even deep space. Nope, it's inside a lab in a tiny little piece of metal. So today, we're going to take a journey to the absolute edge of temperature itself and explore the incredible physics that gets us there. And here is the number, 100 picokelvin. That's the record low temperature for what we call a macroscopic system, an object you can actually see and hold. This record was set at Aalto University's low temperature laboratory. Now, a picokelvin, that's 1 trillionth of a Kelvin. We're talking 0.000000001 degrees above absolute zero. It's just an unbelievably small number. So to put that into perspective, let's look at deep space. The background temperature out there, left over from the Big Bang, is a chilly 2.7 Kelvin. The lab record isn't just a little colder, it is literally billions of times colder. We are so close to absolute zero here that it's almost impossible to wrap your head around it.
This whole endeavor is kind of like a scientific version of climbing Mount Everest, only the summit is impossible to reach. That summit is absolute zero. Minus 273.15 degrees Celsius, it's a fundamental limit in our universe. You can get closer and closer, but you can never, ever actually get there. The story of how we got this close is just fascinating. And get this isn't just some number in a computer simulation. It was achieved in a real, physical thing, a 2-gram piece of a metal called rhodium. And it was the result of this massive, long-term project by an international team of scientists. We're talking about the culmination of decades of work.
So how on earth do you cool something that much? The answer isn't some fancy freezer. It's magnets. To really get how this works, we need to dive into this fundamental battle that's happening at the atomic level, a constant tug-of-war between order and disorder.
Okay, so picture this. Inside a metal like rhodium, the nucleus of every single atom has a property called spin. You can think of it as a microscopic compass needle. At any normal temperature, all that heat energy makes these little compasses go wild, pointing in every random direction imaginable. It's pure chaos. And this randomness, well, it has a scientific name: entropy. Entropy is really just a way to measure disorder. The more feet a system has, the more its atoms jiggle and bounce around, which creates more disorder, and that means higher entropy. So it follows that if you want to lower the temperature, you have to find a way to lower the entropy. You have to create order.
And this is where the core principle comes in. You've got two forces fighting each other. On one side, you have an external magnetic field, which we'll call B. B is like a drill sergeant, shouting at all those tiny compass needles to line up and get information. That creates order. But on the other side, you have temperature, T, which is constantly trying to mess things up and create chaos. The whole state of the system really just boils down to the ratio between them, B over T. If you can control that ratio, you can control the temperature.
So here's the clever trick scientists use. First, they hit the rhodium with a massive magnetic field. That snaps all those little spins into alignment. Now, that process of creating order actually releases a little bit of heat, which they carefully pump away with a pre-cooler. Step 2, they completely isolate the sample from everything else. Think of it like putting it in the world's best thermos. No more heat can get in. And then for the grand finale, they slowly turn the magnetic field off. With the drill sergeant gone, the spans want to go back to being chaotic. But to do that, they need energy. And the only place they can get it from is the vibrations of the metal atoms themselves. So they literally suck the heat right out of the system, causing the temperature to plummet. This whole process is called adiabatic demagnetization. And as you can imagine, it requires an absolutely incredible piece of hardware. This is not something you just buy off the shelf. It's a custom-built machine, and running it requires an unbelievable amount of patience. And here it is, the heart of the beast. It's called a cryostat, and it's basically a refrigerator inside another refrigerator. The outer layers get it cold, then a specialized dilution refrigerator takes it down to just a few thousandths of a degree. But that final, incredible push into the picokelvin range, that comes from 2 of those magnetic cooling stages we just talked about, working one after the other to get colder and colder and colder.
And if you think this is a quick thing, just look at this timeline. You don't just flip a switch. Pre-cooling the system can take several days. Then the final demagnetization, where the magic happens, can take up to a full day because you have to do it super slowly. And once you finally hit that record temperature, you might only have a few days or weeks to actually run your experiments before the whole thing starts warming up again. Choosing the right material is also a huge deal. A lot of metals become superconductors at these low temperatures, and that really messes with the magnetic fields you need. Others have funky crystal structures that create their own internal fields, which stops you from getting super cold. So, after ruling out a bunch of candidates, rhodium and its cousin copper ended up being the best choices for the job.
So this all leads to the big question, right? Why go through all this trouble? Is it really just about setting a record? Well, no, not at all. Pushing things to these absolute extremes opens up a brand new window into the fundamental laws of physics. It lets us see how matter behaves in ways we could never, ever see otherwise. At these insane temperatures, all the usual thermal noise is gone. It's quiet. And in that quiet, the incredibly subtle interactions between the nuclear spins, they become the main event. Scientists get to study totally new kinds of magnetism, explore how it interacts with superconductivity, and just watch the bizarre collective behaviors that pop up when quantum mechanics is the only game in town. And sometimes, the universe throws you a total curveball. Everyone expected that the rhodium nuclei would eventually just freeze into a nice, ordered magnetic state. But they didn't. Even down at 100 picokelvin, they stayed in this strange, collective, but still disordered state, revealing new physics nobody had predicted. That's the real goal here. Not just setting records, but making discoveries that challenge everything we think we know. All right, now prepare to have your mind bent a little, because using this exact same magnetic trick, scientists can explore a concept that sounds like it's straight out of science fiction: negative absolute temperature. So you have to ask the question, is there anything colder than absolute zero? I mean, the laws of physics say you can't even reach absolute zero. So what if you could somehow go beyond it? Well, the answer is a paradox. In this very specific system of nuclear spins, a negative temperature isn't actually colder than zero. As the researchers themselves explain, it's actually hotter than any positive temperature. It describes a weird situation where most of the particles are in a high energy state instead of a low energy one, the complete reverse of normal matter. Now, this doesn't break any laws of physics. It's a special case that can only happen in systems, like these nuclear spins, that have a maximum possible energy. Think of it like a pyramid. Normally, all the blocks are at the bottom, the lowest energy state. A negative temperature is like perfectly balancing that entire pyramid on its pointy tip. It's a super high energy, unstable state that desperately wants to fall over and dump its energy everywhere. It's not cold at all. It's insanely hot. And of course, the same team that set the record for the lowest positive temperature also set the record for the highest negative temperature, minus 750 picokelvin. It just shows the incredible level of control they have over this quantum system. So in the end, by building these ultimate refrigerators, scientists aren't just exploring the edge of cold. They're probing the deepest, weirdest quantum nature of matter and energy. From the coldest it can possibly be to these bizarre states that are hotter than hot. It really makes you wonder, what other fundamental secrets of the universe are out there just waiting for us to get cold enough or hot enough to find them?